Hi, my name is Adelbert Chang. I am a software engineer at Target, and today I'm here to talk to you guys about microservice architectures from a programming languages perspective. This talk is pretty special for me because it combines sort of the two main interests I've had in computer science for the past couple of years. I was trained as sort of a systems person in college, and after college I got into the more programming languages, functional programming realm of things. This is something I've been thinking especially a lot about in the past couple years at my new role, in my sort of semi-new role of doing deployment infrastructure at Target, because it sort of combines the beauty of a lot of the programming languages work that I'm really interested in with the realities and interesting problems that I like to sort of solve and deal with in terms of running microservices at scale. So I've given a couple talks on a related topic the past couple years on a particular system called Nelson, which I'll talk briefly about today. But this talk is mostly centered around more general ideas of how I can see or how I view opportunities for programming language related topics to affect what is often seen as like a completely separate domain of microservices and sort of systems level work. So to start things off, I want to sort of talk a little bit about how we got to microservices, right? So in the past, a lot of applications were written in what is now referred to as monolithic architectures. And despite this sort of scary sounding name, there were a lot of pros to writing software in this way, right? This was sort of a very natural way to start a project off. You start with maybe like a very simple feature, and then as you need more and more features, we would just add more and more code on top of it. And so one of the nice benefits of writing code in this way, of having everything sort of in a single language, in the same repo, linked together, deployed together, is that it makes it very easy to call other components, right? Because everything is sort of compiled together. If I am working on a feature and someone else is working on another feature, I can just sort of make a function call and then that's all I have to do. So calling other components and sort of coordinating features is pretty easy in this model. One of the other benefits you get is what I would call synchronized deployments. So sort of, again, working on different features with other teams. Because everything is sort of linked together and if we're, say, in a statically typed language, I can sort of just make a function call, make sure everything type checks, even maybe have just a stub or a function signature, and I can just compile, I can just type check against that while another team actually implements it. And I can make sure that when I'm deploying, or at least when I'm developing, that sort of everyone is in its place, and I don't have to really worry about like, is that team not ready, or is this team not ready, or anything like that. And so one of the big benefits we get is sort of this safety in terms of deployment, where I know because everyone's sort of in the same repo, everyone's evolving in lockstep, everyone's synchronized in the same code base, I know where all the players are. Of course, monolithic architectures do have downsides, right? So that's sort of what led to the development of microservice architectures. So a big downside of monolithic architectures is sort of deployments being dangerous along a different axis, right? So I just mentioned deployments being safe because everyone's synchronized, but in a different sense, deployments are often dangerous because if we think about, say, we have our monolithic application deployed somewhere in the world, and I'm going to go and work on a new feature, take a couple days away, write the code, merge it to master, and now I want to deploy it. In a monolithic architecture, we can no longer say, give me, I want the current state of the world, and then keep everything the same except for just my chunk of code, right? Because over the past couple days or weeks or however long it took us to develop this, not only was I working on my feature, but other teams were working on their features. And so when it comes time to deploy the code, it's no longer just the delta that I introduced, but it's also the delta that all the other teams introduced. And so now we're talking about deploying several features at once, and typically this means it's a pretty dangerous deployment, and this tends to translate organizationally into a lot of process, a lot of bureaucracy in terms of figuring out how to actually deploy the thing, which leads to slow deploys, which the slower you take to deploy, it's sort of like a vicious cycle. Other people are working on their code, and everything compounds. So there's dangerous deployments along that axis. And then another big con of sort of monolithic architectures is it's much harder to talk about scaling, right? If we think about maybe a social network service or some sort of messaging service, we'll have a lot of different moving pieces, each of which have different deployment needs and have different scaling needs. The component that needs to talk to the database will need to scale independently of the component that's responsible for instant messaging, which will scale differently compared to the UI. And in a monolithic architecture, it's much harder to talk about this than say, a microservices architecture. So because of these cons, the industry over the past several years has started trending towards, or not even trending, we're sort of there already, sort of just converging on making everything microservices, right? Every sort of logical component becomes its own little microservice. And for those who aren't familiar, the idea is essentially that each logical component gets its own deployment story, essentially. You can think of these as network-separated components, each which do a very specific thing. So you'll have one microservices that's responsible for maybe just displaying the newsfeed, and you have one microservice that's just for figuring out who your friends are, and you have another that's running the ML for friend recommendation. And so in this model, what we get is very modular deployments. So because everything is now gets its own deployment story, the team that's working on, say, friend recommendations can sort of make code changes just to their part of the code base and be more or less confident that they don't have to sort of share the deployment burden with the team that's maybe making changes to the friend recommendation system. With this model, we also solve the problem of having things being able to scale differently, right? Because everything is now network separated and presumably behind something like their own load balancer. My database access service can have however many instances it needs, and that can be independent of my newsfeed service, which maybe has like less scaling needs. So a lot of these pros of microservices architectures are designed to solve what were the cons of monolithic architectures, right? Now, because everything has its own deployment story, different teams can work on their own products, they can deploy at their own cadence, and no one sort of has to coordinate with each other and make sure no one's stepping on each other's toes. However, there are also, with microservice architectures, there are also a lot of cons. And what I think is particularly interesting is a lot of the cons associated with microservice architectures aren't really cons that we saw in the monolithic architectures. And so while microservices bring a lot of benefits in terms of being able to run an organization at scale and develop a product with several features at scale, it does introduce some problems that I think need to be addressed. And that's sort of what the topic of this talk is going to be about. So just for the sake of discussion, I'm going to focus on like a very simple portion of our little microservices graph. And so earlier I mentioned that the whole idea of microservices is you now have these different logical components separated by the network. And so it's no longer just a case where we can just like make a function call because everything is linked together. We're now talking about things that are separated, that are running in sort of different machines maybe. And so not only do we have to care about our own application or our own microservice when we're developing a new feature, but we have to make sure that everyone else that we depend on is sort of ready to go. So we need to sort of like figure out what are the dependencies that we need. Maybe if we're writing a social networking service again, I have to make sure the team that's responsible for the newsfeed service and for the friend recommendation service is ready to go. And depending on sort of what language they're written in or different organizational needs, I may need to have to also write a client to talk to that service over the network. So this is something that we didn't have to do in a monolithic architecture. Not only do we have to be able to enumerate these dependencies, but we now also have to talk about if these services already exist, do they have all the features that we need? Are they ready to handle the scale that we're about to hit them at? This is a problem I've hit before where I'm depending on some sort of service that was written for one use case, and suddenly I'm spinning up this massive MapReduce job that's hitting it with tens or thousands of containers, and they can't handle the scale and crash. So it's no longer the case where I can just sort of, because everyone is in the same code base, that I can just like type check and see if it works. I now have to make sure before I deploy that everyone else is deployed and ready to go as well. On a similar axis, just enumerating my dependencies isn't all I need to do, right? Now I need to figure out, because we're network separated, how do I actually talk to them? And so this means not only figuring out what IP address they live at, but also things like what's the network protocol we're going to speak? Are we going to do like JSON over REST? Are we going to do RPC? Are we going to be separated by a Kafka queue? A bunch of these questions started rising. We also now, because we're separated by network, we have to answer a lot of questions that we didn't have to in a monolithic architecture. So things like, how do we handle network partitions? What do we do if a service goes down? What do we do if a service has like an intermittent outage if it's upgrading? And a lot of the usual distributed systems concerns that we normally wouldn't have to think about if everything was sort of linked together. So a lot of the issues we are seeing in microservices right now, and a lot of the sort of work we're seeing in terms of like cluster scheduling and service discovery systems and credentials provisioning are all sort of motivated by, okay, we have this microservices architecture, but now we need to talk about like all this tooling we need that we didn't really need before to make everything sort of work together as a cohesive whole. So, to sort of narrow the topic of discussion today, I want to focus on one very specific thing that sort of comes up a lot that microservices sort of have to deal with. A sort of thing that we didn't have to really deal with in a monolithic deployment, which is service upgrades. So same sort of subgraphs that we're going to be looking at. I'm color coding them now so I can refer to them by their color. We have like a purple service that depends on the blue and green service, and the green service transitively depends on this, I don't know, teal service. So we can assume everything is working more or less fine now. And then at some point, usually, let's say the owner of the blue service wants to do an upgrade for whatever reason. They're adding a new feature, or they want to make a protocol change, or something's happening. And so typically the way this is done with what's called a rolling upgrade. So I mentioned earlier that a lot of these microservices are separated or are back, sort of present this facade of a virtual IP address or a load balancer. And so what happens when the blue service goes to do an upgrade is they will typically say, bring down an old version, or bring up a new version, or a new instance of the new version, and then shut down an old instance, and then bring up a second instance of the new version, and then shut down another instance of the old version, and to keep doing that until eventually the only thing that exists is the new one, and everyone is suddenly pointing at the new version of the service. And so this is kind of, you can think of this sort of as like a mutable deployment, where all the dependencies or all the services that dependent on that service have to sort of be ready for that upgrade automatically, right? Because this isn't something they can opt out of. It's sort of just happening mutably, and everyone needs to just be ready for that change. Now, in this particular graph where you maybe only have one dependent, we can sort of talk to them before we deploy and just say like, hey, we're going to make an upgrade. But if we're thinking about sort of running microservices at scale, when we're talking about tens, hundreds, thousands of microservices, this quickly becomes a problem. And not infrequently, either intentionally or on purpose, because there's a bug with the client, or there's a bug with the server, or there's a bug in the deployment process, things get affected, services crash, and whoever is on call gets paged and doesn't have a good time. And so this is just like sort of a simple case. Like I mentioned earlier, if we think about orchestrating all these microservices with several dependents and with a lot of transitive dependencies, this quickly becomes a nightmare in terms of like, how can I be confident when I upgrade my service that I don't sort of break the entire graph? So let's dive a little bit deeper, right? Earlier I mentioned that like when someone deploys a new version, some things can break. So what specifically can break? So I'm going to talk about a sort of common upgrade pattern, which is protocol changes. So in a monolithic architecture, where everything is linked, and let's say we have static types, let's say we have some function, some other component that, say, has this type signature, takes an average of 2 numbers. And if we call that function incorrectly with incorrect types, then we'll get a compile error. And then we sort of know, we fix it, and then we move on. Maybe we're doing dynamic linking, we'll find the error a little bit later, or if we're using the dynamic type language. But at some point, we don't make it very far. However, now that we're talking about components that are separated by a network, we suddenly have to think about, all right, what is the protocol that we're going to use to speak to each other? So usually what happens is, let's say we have a blue service that says, I'm going to expect as input some JSON object with a name field, and this will typically be documented maybe in like a README or something, and then the purple service will have to like understand that when it calls the blue service, I'm going to send some JSON object with that particular format. And so this works for a while, and this maybe for like the first couple days of deployment, this is fine. And then as usual, upgrades happen, and what I've seen very frequently happen is these upgrades, for whatever reason, tend to either accidentally or on purpose make backwards incompatible changes. And so this new version of the blue service comes along, does a mutable deploy, everyone unknowingly switches to this new version. And so the next time it makes the call, sort of assuming that it has the same schema, what we get is an error that sort of just rejects a request. And this has happened several times, both to me personally and to people around me, where something sort of just works for like even weeks, and then what happened one time was I went on vacation for 2 weeks, came back, and things were broken, and I didn't even touch my service. And that's because sort of one of my dependencies accidentally deployed a breaking change to their protocol. And so this is sort of the trade-off we have when we're talking about microservices communicating over network, is a lot of these, we sort of lose a lot of this functionality in terms of having everything linked together, having everything synchronized, having a type system to guard us. Now things are a lot more dynamic, and while we do gain a lot in terms of like being able to deploy things agilely and scale things independently, we lose a lot of sort of safety. And of course, like this is just like for each sort of client server, not only are we talking about protocols or schemas for making the request, but also sort of parsing the response that we might get back from the server. All right. So hopefully I've convinced you guys that we've gained a lot moving to microservices architecture, but we've also lost a lot in terms of like how safe we can be, in terms of doing upgrades, in terms of handling, communicating over a network, in terms of the network protocol that we're all going to speak. And so there's a lot of problems with this microservice architecture, and especially when we're talking about running them at scale with tens, hundreds, thousands of microservices, we want to be able to make sense of this world, right? We can just like provision an AWS account or like run a Kubernetes cluster, and everyone just sort of deploys their own Docker image or whatever and hopes for the best. But what we want to be able to do is gain a lot of sort of the safety and tooling that we get with monolithic architectures, in terms of everyone knows that the dependencies are in place. We can upgrade sort of without worry. We can, if someone changes their schema or changes their type signature, we can find out before it's too late. So looking at, if we just treat deploying microservices as like deploying disparate services, this can seem like a very daunting task. Because if I say deploy the ping service, I have no idea like who's going to call me. I don't really know if the blue service that I depend on is ready for me or not. So this can be pretty scary. Thankfully, especially in industry, we can sort of assume this presence of a deployment service. And so for each in industry, for each organization, not only do we have each team working on the microservice for their feature, but typically there's one team called the deployment team or a services team whose job is to take code from a GitHub repo or whatever repo to deploy it on a machine somewhere. What my VP used to describe as making code get the actual chips on a server farm hot. And so the way a deployment service works is it sort of acts as a proxy between getting code that's maybe bundled as a tarball or a jar or a Docker image to deployed on an actual cluster somewhere and doing useful work. So let's say we want to deploy this salmon color service. It will go to the deployment service either via an API or a UI and say, I want to describe like what it is, what the tarball address is, what command to run, and sort of how to deploy it. And the deployment service will be like, OK, I'll deploy you, and then it'll connect to its dependencies. And then so different services will come in, declare themselves, get deployed, and then connect. Now, usually what the deployment service does is it just sort of acts pretty much like a proxy. Tell me what you are, what to run, where to run you, and that's all I do. But what we can do is, because everything has to flow through this deployment service, we can sort of require that everything that is deployed to declare additional information to us that we can then leverage to provide useful tooling to service owners. So what I'm sort of getting at is, instead of thinking about this microservices graph and this deployment service as deploying disparate services, we can think of it kind of like a language runtime, right? So if we think about language runtimes, it's sort of about, we know you're going to create a bunch of these objects have references to each other, and with some restrictions, I'm able to sort of manage this, I guess, object graph for you. I know what's live, what's dead, what's safe to destroy, and if, I mean, like, and sort of the difference between like a garbage collected language and a not garbage collected language, where you're sort of managing memory yourself, you have to be very careful, right? Think about the difference between, say, C versus a language like Scala or Java. And so what we can try to do is, because we can safely assume we have this deployment service, we can, instead of thinking of it as just a proxy for getting our code onto a cluster, we can think of it almost as like a microservices or a deployment runtime that does for microservices what, say, VMs do for languages. So let's explore this. What do we need? So the most basic thing we need to think about when describing a sort of deployment runtime is, what are the objects that we're handling? What are sort of the entities that we're going to be managing and providing services to? So in a language runtime, we have to think about objects and like, what does it mean to create an object? For services, we can think of the objects as services, and then creating an object is sort of like deploying a service to an actual machine somewhere. The next step we then have to think about is reference tracking. So what depends on what things do what fields do different objects have. From a service perspective, we can think about this as both service dependencies, so that's sort of like referencing other objects in the system. So maybe my service depends on 2 or 3 other services. And then for sort of fields of an object, I can think of it as my service advertising different resources. So maybe my service handles anything related to friends, including what the current list of friends this person has is, as well as what friends we may recommend for this person, right? So I can advertise different resources to people. Assuming we're talking about a garbage collected language runtime, garbage collection in sort of a deployment runtime can be thought about as deprecating and destroying old legacy services. And then that sort of begs the question of, what exactly does legacy service mean? How do you determine what is no longer used? And we'll talk about that. And the last thing I want to cover also is this notion of type safety, not really a language runtime thing per se, but sort of just maybe you can think of it as like memory bounds checking or something. Where in deployment runtime, we can think of this as schema checking and having some sort of system to talk about schema evolution. And there's a bunch of different other sort of analogs we can think about, where there's one thing in a language runtime and another, and what the analog of that is in a deployment runtime. But these are the ones I'm just going to cover today. And I'd be happy to talk with anyone who has different thoughts on this after the talk. So let's sort of explore what a deployment runtime might look like. So let's start with like a clean slate cluster with nothing deployed at all. And we want to deploy sort of this blue service. It's the very first service we're going to deploy. Now, besides just requiring it to declare what the Docker image is and what command and where to run it, we're also going to make it declare the name of itself, which is going to be sort of like the identifying thing of this service, so that other services want to depend on it can reference it. And then also, don't have it listed here, but we can require it to also declare the version of itself. So you can think about the blue service 0.1.0. Deployment service, the deployment runtime will then go ahead and deploy that service as usual, but also enter into some database that may maintain that we now have the dark blue service at 0.1 deployed somewhere. Then we can imagine the pink service comes in, and it's going to declare not only that its name is pink service and how to deploy it, but also in that fourth line there, that depends on the dark blue service at 0.1. And here we can already begin seeing that with just a little bit more information, and we can sort of think about this sort of manifest file that we're declaring to a runtime as sort of the object constructor fields. But we can see, like, with this information now, we can say, oh, the pink service depends on this dark blue service. I'm going to look at my database to make sure the dark blue service exists before I go ahead and deploy the pink service. If it doesn't exist, then I can reject the deployment right now, as opposed to deploying it sort of blindly and then hoping for the best. So even with just a little bit more information that we're providing to the deployment runtime, we are sort of getting some benefits that we otherwise would not be able to get. So assuming everything works out, we deploy the pink service. We can connect it even automatically to the blue service if we wanted to, using a service discovery system like etcd or Zookeeper or Console, and sort of provide a lot of this convenience tooling for the pink service to just locate where in the cluster the blue service is. And then we can keep doing this for other services. So we have a cyan service that depends on the pink service at 0.2. Everything checks out. It gets deployed, connects. and keep doing this slowly but surely until we sort of get a full or some semblance of a service graph. So what we've gained now is just by requiring things to declare a little bit more information at deployment time, we can do things like make sure all the dependencies exist, which we couldn't really get without a system like this. We can make it very easy for services to locate their dependencies in terms of like what their cluster IP address is, because the deployment runtime, because it knows what the state of the world is, it can sort of have in its database like, okay, the dark blue service at 0.1 is at this IP address. And so when the pink service says, I want to talk to the dark blue service at 0.1, it can use maybe something like environment variables to say this is where it's located, as opposed to having to use some sort of what is typically done out of band, like find out what the virtual IP address is, insert it into a config file, and then deploy it and hope for the best. So now we can, with this sort of primitive runtime, we can create and sort of track dependencies. Now we can also talk about versioning services. So earlier in the talk, I was talking about how sort of mutable deployments can be very dangerous and can make people a bit antsy. And so we can talk about how having a deployment runtime can help solve that. So let's focus on a subset of the graph here. And what we're going to do is focus on that, I guess, cyan, light bluish service towards the bottom left there. So the service owners for that service are going to want to upgrade. And so what they're going to do is they're going to, that service is going to go to deployment runtime, say I am the light blue service at maybe 0.3 now as opposed to 0.2. The deployment runtime says, OK. It's going to deploy it, connect it to its dependency, and then that's where it stops. Earlier, I mentioned that sort of in a mutable deployment model, the new version would slowly sort of take the place of the old version. But what we can imagine is this system, instead of just doing a mutable replacement, is just going to deploy alongside. So at this point, the deployment service is done, and we have both the old and the new version coexisting. And this is fine this is fine because earlier I mentioned that among the things the deployment runtime can do is provision maybe an IP address per deployment it makes. And so we can just allocate a different IP address for this new service, and the old one keeps its IP address. And so everyone that's connected to the old one sort of continues to work. This then begs the question of how do we actually make the dependence of the cyan service actually connect to the new version, because we want to eventually roll forward to the new version and kill the old one. And so what we can then say is, well, if you want to actually, once the pink service is ready to connect to the new version, it's going to redeploy itself. But now, instead of this, in its dependencies list, instead of saying I depend on 0.2 of the blue service, I'm going to say the pink service will say I depend on 0.3 of this new service. And so deployment runtime will check to make sure it exists, everything works out, and it's going to now connect to using sort of maybe the service discovery system that the runtime provides, connect to the new version as opposed to the old version. And then we can do that for the green service as well. The green decides that it's ready to move on to the new version of the pink service, so it's going to redeploy itself, redeclare its dependencies, and connect to the new versions of its dependencies. And so at each stage of this deployment, of this new sort of deployment model, you can think of it as like immutable deployments. The old version and the new version are always coexisting, and until a particular service has explicitly decided that it's ready to move on and roll forward to the new version of a dependency, everything is sort of coexisting in the cluster at the same time, assuming we have enough resources. So that's the state of the graph right now. We have a bunch of duplicates. Now we need to talk about how do we garbage collect old services, right? So at some point, we're going to be at a stage where we're comfortable shutting down the old version of the green service, the old version of the pink service, the old version of the blue service. And one of the benefits of knowing what the state of the world is in our deployment runtime is because we know what the full service graph is, because everyone's declaring what their dependencies are, we know what order we need to shut things down in, right? Basically, this is kind of like topological sorting. We have to shut them down in the order in which a particular service doesn't have dependencies. So in this case, we can shut down the green service first, because we're for whatever reason confident that the new version of green service is good to go. So we shut down that one, and then we can then shut down the old pink service on the left, and then from there we can shut down the old blue service. Did I miss my animations? I might have. Yes. Okay. And so that's sort of the state of the world that we have there. Now, that sort of establishes the order in which we know how to shut things down, and we sort of, because we have the graph, or I guess the DAG-ish, we know when it's safe to shut down. But we also want to now talk about doing this automatically, right? Both because humans are lazy, or because we just want to make it easier for people to do their job. We want to hopefully have a notion of automatic garbage collection, sort of like a GC language as opposed to a manually managed memory. And so we need to have a notion of liveness, right? So in a garbage collector language, we sort of know what active objects are in play and what sort of has the chance of still being used versus objects that are sort of falling out of scope or no longer referenced and can be safely garbage collected. And so we need to sort of have an analog for that in this microservices architecture or in this deployment runtime system. And so one of the ways we can accomplish that is to say, everything that's live must be either load balanced or load balanced externally, so like reachable from like outside the cluster, or it must be reachable from something that is reachable from outside the cluster. So in this case, we can sort of imagine that we have an externally exposed service, the green service, and that sort of represents maybe the UI or the entry point into our social media website or whatever. And then from there, we can sort of trace in the graph which services are reachable from my green service. And so the things that are highlighted that are sort of bolded or are not opaque or not transparent are the ones that are reachable. And so we can now establish that we have a couple services there that actually aren't reachable from an external IP address. And then from there, we know the order in which we can shut things down. So the first ones that go are that yellow service, and then we can shut down the blue one and the orange one. And then that's the state of our service graph from there. Right? So this is sort of like the mark and sweep algorithm that we see in garbage collector languages, where we start from what's live, which in this case are what's load balanced, sort of scan the graph and mark which ones aren't reachable, and then we can have some other process that periodically wakes up, finds out which ones aren't reachable, and then shuts those down. So everything I just described for that sort of deployment runtime in terms of like declaring the name and version of yourself and of your dependencies, of providing service discovery, of doing sort of explicitly managed like service upgrades and stuff like that, that exists today in a system called Nelson. And so Nelson is an open source project that was originally created at Verizon Labs. It's now deployed at a couple other companies. It's an active open source project. I'm actually one of the maintainers of it. It's undergoing more evolution to make the system more flexible and widely applicable. Talk to me if you're interested in hearing more. But everything I described today exists in some form or another in Nelson. And so these ideas, while are sort of interesting to think about, and we can think about taking it in different directions, it does exist in the real world, has been tested at scale, and actually does provide a lot of utility. So that's sort of the story of managing the service graph like as a whole. I want to sort of take a step back or talk about something more specific that I mentioned earlier in terms of schema evolution and sort of type checking schemas. So I mentioned earlier that a very common problem, especially when we're talking about sort of these unchecked protocol languages like JSON over REST, is that one service, when it upgrades, will either on purpose or accidentally make a backwards or forwards incompatible change that sort of breaks clients, especially in a mutable deployment model. Right, so in this case, it suddenly expected an age field now, and this client, for whatever reason, forgot to provide it or doesn't provide it, and then it fails at runtime. So this problem is particularly exacerbated in a transport system like JSON, because JSON sort of doesn't really have a notion of a schema, right? JSON is pretty fragile. It's hard to keep track of. People typically will just like sort of document this like in some sort of README somewhere or some sort of documentation website that this is the format of the JSON. This is an example JSON blob I'm going to send, but there's no sort of system or suite of tools that you can use to say this is the schema I'm going to use, and there's no sort of cohesive set of rules that dictate what's sort of a forwards compatible change, what's a backwards compatible change, what happens if we rename keys and stuff like that. And so this is where a recent trend towards interface definition languages, or IDLs, come in. So if you've heard of systems like protocol buffers, or Thrift, or Avro, or Cap'n Proto, those are all IDLs. And IDLs at a high level, or sort of really quick, you can think of as a DSL that's just for specifying types. It's a very specific kind of DSL that all you can do is describe types, maybe with some annotations to help determine how to actually serialize it to talk over a network. And because these are very limited, we can provide additional, because we're not sort of talking about any sort of like function signatures or like recursion or anything, and we're just declaring types, we can provide some additional power that we might not be able to get in like a traditional programming language. So one of the most basic things we want to be able to do is to take an ideal schema, so in this case like a person schema, and then generate code for it. And so the idea is we will write the schema once in this sort of, in this case, protocol buffers, and then we can emit code both for, say, a Java programming language, or we can also emit code for Python. And so what we can think about is, instead of having services just sort of document somewhere that I want a JSON field with a name attribute, I'm going to actually advertise this schema, and then anyone who wants to call my service can take that schema and generate it for whatever language they want, and then call the service from there. And so the idea here is we'll have one language used just to describe schemas, and then we'll write a sort of compiler that takes that sort of that language and compiles it for like Java, for Python, Scala, Haskell, Rust, whatever. And then from then on, any sort of schema written in that language, we can just code gen and then call immediately without having to sort of handcraft what the serialization or deserialization is. Another thing that we can do with IDLs that we wouldn't be able to do with JSON is we can now have a system for talking about what does it mean to have schema compatibility in either the forwards direction or in the backwards direction. So talking about schema evolution, just for some definitions. So backwards compatibility basically means that it's very useful in, say, processing historical data, right? If you think about like a MapReduce job or a Spark job where you have a lot of historical data, backwards compatibility means if you release a new version that's backwards compatible, you should be able to use the new schema but still be able to read historical data. You can also think about, and so what that usually means is you can say delete fields. So if I have historical data that has, say, both a name field and an age field, and in my new schema says I only want a name field, you can still sort of parse old data because you're just going to drop the age field anyways. So that's the notion of backwards compatible. And so we can now talk about sort of, instead of just saying, like, for this JSON blob, we're going to drop these or whatever, we can have a system for checking if something's backwards compatible. And typically, protocol buffers and Thrift and Avro come with their own suite of tools to, given two schemas, will tell you whether or not they're compatible or not. We can also think about forwards compatibility. So that's sort of like if I have like a job pipeline, if I have this thing that's producing a person struct where it contains just a name, and I have a consumer that's just going to use that name and like do something with it. I can make a forwards compatible change where I add a field to the thing producing code, producing the record. So maybe I add an age field, but my consumer will still continue to work because it can just sort of safely ignore what the age field is. And then we can also talk about full compatibility, which is sort of a schema change that's both forwards and backwards compatible. And so a lot of these tools that I've been talking about, protocol buffers, Avro, and Thrift, have tools because they're now like in their own language, and they have sort of a formal spec of what you can declare and what you can do and how they're serialized. We can now talk about if you make a schema change, what if the schema change? We have a way of ascertaining whether or not that schema change was backwards compatible, forwards compatible, or fully compatible. And depending on where you are in the pipeline, if you have dependencies or if you have dependents and how things are working in your system, if it's like a job or a pipeline or a microservice, we can sort of stop that. We can even build it into, say, the deployment runtime that we described earlier. And sort of when we deploy a new version of our service, if it's, say, going from 0.2.0 to 0.2.1, and I did a schema change, we can make the deployment service run this checker, and if it's not compatible, then reject the deployment. If it is compatible, then go ahead and deploy. We can actually take this idea a bit further and talk about contract languages, right? So earlier I mentioned schema languages are sort of just for describing types, but typically types aren't strictly enough to describe what we want. If you think about, say, that person struct, a person will have a name and an age, but an age maybe it's not just an integer, right? We want the age to be a positive integer. It's not really a negative age that we can have. And so this is where sort of contract checkers come in, where we describe dynamic properties of the data flowing through the system. And there's been prior work on this. So those are two papers that I read recently. There's a ton of other work around contract languages. Another cool thing that a lot of contract languages have, so like WIP, for instance, has this notion of a blame system, where not only at runtime will it detect when something's violated a contract, and like maybe the age field of the person struct that's flowing through the network is a negative, but can also sort of figure out who's to blame for this issue. Is it the client that's having the fault? Is it the server that's having the fault? And again, we can think about maybe a language runtime that understands what a contract system is. We can think about then dynamically when I deploy this thing, and if something breaks, not only do I know where it's broken, but also what version it broke and who's to blame for that breakage. To that end, I've been working on a project with the Composable Systems Lab at CMU. And so we're actually working on a system very similar to what I just described, where we have IDLs and we have contract languages, and we're talking about like sort of full microservice graph. How can we build a language from the ground up to sort of have tunable degrees of like, do you want to just check the IDLs, in which case maybe we just check those statically and just maybe at CI time, or do you want to maybe have a fully fledged contract language where we can not only check a subset of it at CI time, but also insert like a proxy into the network to sort of check all the messages flowing and make sure everyone's on the same page. So that's a project I've been working on. This is actually a pretty rich area of projects that sort of have this idea of using programming languages or having some sort of runtime support to support different kinds of systems. So I talked a little bit about Nelson, which is sort of providing a runtime for just talking about deployments. We have a project called Unison, which is sort of rethinking how you program the cloud. We have projects like LASP and Partisan, which are, so LASP is a suite of Erlang libraries for sort of providing language level support for programming distributed systems. Partisan, you can think of it as a runtime system for scaling actor-based applications. Or Leans is a project from Microsoft Research for a .NET suite of languages that also sort of provides a runtime-like system for programming distributed systems. So I think I'm running short. Am I over time, or do I still have? Okay. So I do think, despite the fact that sort of programming languages and systems are often seen as separate fields, I do believe that there's a lot of interesting work we can do at the intersection, and there's different sort of degrees in which they intersect that can be very useful and help both sides of the field. That's all I had for you guys today. Hope that was interesting, and yeah.
So if you have microservices that maybe you can't garbage collect yet because they're still reachable in your graph from the root node, have you done any kind of concrete measurements on how much wastage there is on having multiple versions of the same service running at the same time, as opposed to enforcing that everyone must migrate to the next version at the same time?
Are you asking if? So, can you rephrase your question maybe?
Yeah, sure. So if you have version 0.1 and 0.2 of a microservice running, then that's going to consume more resources, be more wasteful than just running one thing at the same time.
Yeah.
Do you have any have you done any measurements in your experience on how much overhead that is in practice, or how much wastage there is?
I haven't done any measurements myself, but one thing sort of not semi-related to what you're talking about is to sort of encourage people to eventually move over to a new service so we don't always have to maintain 2 or 3 or however many duplicates or old versions of a particular service. One thing that Nelson does is to have service owners of, say, the blue service say, I'm deprecating 0.1 of my service. And what that does is then any subsequent deploys of like a dependent that says, I want to depend on 0.1 of the blue service, that will actually be rejected by the deployment by Nelson. And so that's another thing that we can do because we have full knowledge. We have like this rich information about the service graph now. But in terms of like concrete measurements, Nelson has enough information to do those kind of measurements, but of course it's going to vary drastically depending on your cluster size and your microservices resource needs and how many replicas you have and stuff like that.
What would your recommendation be on dealing with when you have a dependency that leads to multiple dependencies that have changed? What do you do in those circumstances with deployment orchestration?
If we have multiple dependencies that have changed?
Yeah, multiple dependencies that have changed, or multiple paths to the same dependency.
In the case of multiple dependencies that have changed, it would just be the same. If you wanted to upgrade all of them at once for whatever reason, you would just bump the version and sort of when you declare like I want to deploy a new version of my service, I'm now ready to switch to all the latest versions of my dependencies. I don't know. In terms of having multiple paths in a microservice architecture, that might, depending on sort of how things are set up, that may or may not cause issues. So this is sort of a known problem where if things, are you thinking about like if you have a transitive path to an old version, but you directly depend on a new version of a service?
Yes, I was thinking about having, independent, like a transitive dependency and a direct dependency, for example. Or 2 indirect dependencies actually, because then you might consider upgrading each of them independently and then upgrading, like having even separate deployments of the top level deployment unit for each of the, well, you get the Cartesian product of all the changes below.
I'm not too sure what you're asking, but maybe we can talk afterwards, if that helps.
Let's do that.
In the interest of time.
So what about bug fixes in your services? So if I understand correctly, it seems like if you have a bug in a service and you want to fix it, no one else is going to get the fix unless they redeploy a version of their service that says, I am now running on that new fixed one. Is that intentional, or is that a pattern that you would like to have some other way to say, I can sort of transparently deploy bug fix and no one has to know about it?
So I guess this is about Nelson specifically. So the way Nelson handles this is actually it bakes in this notion of semantic versions into services. So there's a major, minor, patch. And so for, I think, minor bumps, then it'll be like sort of, you have to explicitly opt in to upgrade. But then for patch bumps, what I actually do is it'll deploy both, it'll still deploy a copy, but then it'll traffic shift. Because it knows it's a patch bump, and so it should be, in theory, backwards compatible. It'll do a traffic shift over, and then once, while the traffic shift is still in process, people can sort of say like Nelson, they have a CLI tool to say like, oh, this thing looks bad, revert back, traffic shift back to the old one. But if everything looks good, then eventually everything is traffic shifted to the new version, the new version, and then the old one is no longer reachable from a live node, or if it's not, and then it'll be garbage collected. So there is technically, if everyone just only ever used patch versions, then yeah, it would sort of be back to the mutable deployment model. But now we have this, we can now have this granularity where we talk about, is this change backwards compatible versus is it not backwards compatible? And if it's not backwards compatible, I now have a vocabulary for talking about, or at least a system for deploying that without worrying about breaking everyone else.